Periodate oxidations, oxidative cleavage of polyhydroxy compounds. Compounds that have hydroxyl groups on adjacent carbons, that means vicinal diol, undergo oxidative cleavage when they are treated with aqueous periodic acid. The reaction breaks carbon-carbon bonds and produces carbonyl compounds. This is the stoichiometry of oxidative cleavage by periodic acid. You have this carbon-carbon bond and this vicinal diol. You are treating it with HiO4. Then this bond will be broken, and you will get two molecules of ketones in case of this, and HiO3 plus H2O, etc., etc. And what is the important thing, that this OH should not have to be necessarily a cis diol. That means this should not have to be in the same positions or same directions. Now see the reaction course, the transfers of electrons here, and we will come in detail later. When three or more CH-OH groups are contiguous, the internal ones are obtained as formic acid. So that means if you have consecutive 3 CH-OH group, then this middle one will make formic acid. Periodate oxidation of glycerol, for example, gives 2 molar equivalents of formaldehyde and 1 molar equivalent of formic acid. So you have taken this glycerol and you are doing the periodate oxidation. So this will give 2 mole of formaldehyde and 1 mole of formic acid. This middle carbon will form the formic acid. Oxidative cleavage also takes place when an hydroxyl group is adjacent to the carbonyl group of an aldehyde or ketone, but not that of an acid or an ester. Glyceraldehyde yields 2 molar equivalents of formic acid and 1 molar equivalent of formaldehyde, while dihydroxyacetone gives 2 molar equivalents of formaldehyde and 1 molar equivalent of carbon dioxide. So you can check that if you take glyceraldehyde, this will form formic acid, another one formic acid, and one formaldehyde molecule. And if you take dihydroxyacetone, this will form one formaldehyde, this one will form carbon dioxide, and the last one will form another one formaldehyde. Periodic acid does not cleave compounds in which the hydroxyl groups are separated by an intervening CH2 group, nor those in which a hydroxyl group is adjacent to an ether or acetal function. So you can see that here is OH, here is another OH, but periodic acid cannot oxidize this compound because this OH is not on the adjacent carbon. These are being separated by this CH2 group. And in case of this one is the OR, that means OCH3 group, and this one is the OH. So periodic acid cannot oxidize this compound also. Now mechanisms of periodic acid oxidations. So this is the mechanism of vicinal diol. Look at this very carefully. Actually I have some pain in my throat, that's why I am not describing this all. This is in case of alpha hydroxy carbonyl compound. In case of alpha hydroxy, this hydroxyl group will attack the iodine first, and then this water will be eliminated. Then after that this OH will attack this carbonyl group, and after that this CC bond will be broken. So finally you will get an acid and an aldehyde. Now in case of 1,2-dicarbonyl compound, this is much more difficult one. At first this OH will attack this carbonyl compound, then this will form OH. At the same time another one OH will attack this carbonyl group, and this will also form OH. So then the electrons or the bonds will be changed, and this CC bond will be broken. So at last you will get this carboxylic acid and another molecule of carboxylic acid. Two carboxylic acids, but they are not same. If this one is R and this one is R dash, then you will get one R here and another one as R dash. In case of alpha alpha dash, the dihydroxyketone. Okay, this one is the most difficult case. At first this hydroxyl group will attack the iodine. Then one molecule of water will be eliminated. Then another hydroxyl group will attack the carbonyl. And after that this OH, that means this carbonyl is forming OH. So this OH will attack another one periodic acid molecule. And after that this OH, here you can see, after this one, and thereafter this one. So this OH is attacking the iodine. So at last two bond will be broken. Here one CC bond and another one CC bond. So two simultaneous bond will be broken. So at last you will get aldehyde, another one aldehyde, and this H3I4. The products of the periodate reaction may be predicted by replacing each clipped CC bond with OH groups on the carbons. Water is then removed if needed. So this is the small trick for finding the periodate oxidation products. At first, if you see that there is a vicinal diol, just break the carbon-carbon bond. So you are breaking the carbon-carbon bond and then add OH group to each carbon. So at first you are breaking the carbon-carbon bond, then adding OH to both the carbons, and then if you have two hydroxyl groups on the same carbon, then just eliminate 1 mole of water from that. So if you eliminate water, you will get this formaldehyde, and if you eliminate water from this, you will get glyoxylic acid. This one is also similar. In case of this, you have to break these two bonds, because this is an OH, this is keto group, and this is another OH. So all three groups are reactive towards the periodate oxidation. So these two carbon bonds will be broken, and then no, what happens? Okay, I was here. So just break these two bonds and then add OH to all of these carbons, and in the middle carbon there will be 2 OH. In this carbon 2 OH groups will be added, and then eliminate water. So you will get this formaldehyde, carbon dioxide, and another one formaldehyde. So why we are doing this? We can do this because we know that gem diols are usually unstable and they lose water to form carbonyl compounds. So this is the mechanism of that process. If you have a gem diol, that means 2 hydroxyl group on the same carbon, and vicinal diol means 2 hydroxyl group on 2 adjacent carbon. So don't be confused with these two terms. Now this hydrogen will give this bond here and this OH will leave. Actually this OH and this H will make 1 mole of water, 1 molecule of water. How periodic acid could be used to distinguish between an aldohexose and a ketohexose? Oxidation of an aldohexose and a ketohexose would each require 5 moles of HiO4 but give different results. An aldohexose yields 5 moles of formic acid and 1 mole of formaldehyde, whereas a ketohexose yields 3 moles of formic acid and 2 moles of formaldehyde and 1 mole of carbon dioxide. So this is the most important thing. In case of ketohexose, you can get 1 mole of carbon dioxide. Therefore, one can distinguish between an aldohexose and a ketohexose by measuring the formic acid and formaldehyde formed, or simply by identifying gaseous carbon dioxide, which gives a white precipitate of calcium carbonate when passed through lime water. So you can easily detect this carbon dioxide, and from that you can say which one is the ketohexose. Periodic acid oxidation of glucose. So try this yourself. This is very much simple. Just at first break all these bonds and add OH group, then just eliminate water if possible. And this is the periodic acid oxidation of fructose. So that was in case of aldohexose. This is in the case of ketohexose. In case of ketohexose, you are getting 1 molecule of carbon dioxide because of this carbonyl group. How periodic acid can be used to distinguish between a 6-membered and a 5-membered glucoside ring? So this is your methyl alpha or beta D glucopyranoside. That means simply methyl glucopyranoside. And if you just oxidize it with periodic acid, you will get a dialdehyde. A dialdehyde. That means here and here. These two bonds are being broken, and then you are getting a dialdehyde and formic acid. This middle carbon will form the formic acid. And if you acidify this dialdehyde, you will get this glyceraldehyde, glyoxal, and methanol. Methyl glycoside consumes 2 molar equivalents of periodic acid and produces 1 molar equivalent of formic acid and 1 molar equivalent of a dialdehyde, which on hydrolysis produces D-glyceraldehyde, glyoxal, and methanol. It demonstrates that the glycoside is a 6-membered ring. That is, this glycoside is methyl alpha or beta D glucopyranose. In case of 5-member ring, methyl glucopyranoside, if you do the periodic acid oxidation, you will get a trialdehyde and formaldehyde. So there will be this bond will break and this one will break. So you will get a trialdehyde and one molecule of formaldehyde. Actually, this one will make the formaldehyde. And then if you hydrolyze this trialdehyde, you will get this, and this. For the 5-membered ring, that is a furanose, 2 molar equivalents of periodic acid would be required, but 1 molar equivalent of formaldehyde and 1 molar equivalent of a trialdehyde, which on hydrolysis would yield hydroxymelonaldehyde, glyoxal, and methanol, would be produced. So by getting these products, by analyzing your products, you can differentiate between a 6-membered ring and a 5-membered ring. Now see this one. You are oxidizing the methyl alpha D glucopyranoside. You are getting this one and this one molecule. This bond and this bond is being broken, but not these two. Okay, these two cannot be oxidized because these two are not a cis diol. Sorry, not cis actually. This OH and this OH are not in the adjacent carbons. They are separated by another one, CH2. So this is not a 1,2 glycol. That's why it is not oxidized. And this is in the case of methyl alpha D fructofuranoside. This and this will be broken. Why alpha D glucopyranose is oxidized by HiO4 more rapidly than the beta ionomer at the 1,2 bond. So at the 1,2 bond, the alpha D glucopyranose is oxidized faster by the periodic acid. Then what is the reason behind it? Alpha D glucopyranose is the cis 1,2 diol and the beta ionomer is the trans 1,2 diol. So periodic acid can oxidize both the cis and trans diol, but as this alpha D glucopyranoside has the cis diol, this will be faster. So since the former can form a cyclic ester with periodic acid and the latter cannot, the former is oxidized more rapidly than the latter. So because of this, as these two are in the cis position, one is in the axial and in case of 2, this is in the equatorial. So these cis diols give a faster reaction. Why D-mannose is oxidized faster than beta-D-glucose by periodic acid? So D-mannose is oxidized faster by the periodic acid than beta-D-glucose. What is the reason behind it? In the more stable alpha ionomer of D-mannopyranose, the OH groups at C2 and C3 are cis to each other. So this OH, C2 and C3, they both are in the up position. This one is the axial up and this one is the equatorial up. So they are in the cis to each other. Whereas in the more stable beta ionomer of D-glucopyranose, no two adjacent OH groups are cis to each other. All these OH groups are trans to each other. Look, this one is the equatorial up, this one is the equatorial down, again this one is the equatorial up, this one is the equatorial down. That's why no two hydroxyl groups are cis to each other. Since a cis 1,2 diol can form a cyclic ester with periodic acid, alpha D mannopyranose is oxidized more rapidly than beta D glucopyranose. Periodic acid works well in aqueous solutions, and lead tetraacetate, that is PbOAc4, gives good result in organic solvents. Since most simple sugars are highly soluble in water, periodic acid rather than lead tetraacetate is used for their oxidative cleavage. So that's why we use the periodic acid rather using this lead tetraacetate.